All right, welcome back, ladies and gentlemen. Your physics teacher has given you a problem to solve. This is going to be a horizontally launched projectile, and here's your situation. You have the countertop in your physics classroom, and you're rolling a ball off the edge of that countertop. This ball is going to have a horizontal launch velocity in the x direction. The countertop is a certain height above the floor, and your physics teacher wants to know, well, where does this thing land? What is the horizontal range of this projectile? It's coming to one of these things, right? Okay, so that's the situation. Now, obviously, there's going to have to be some information you know, but this is our goal, finding that range. In this situation, let's say you know that launch velocity, and there's one or two ways to actually get that from observation up here on the horizontal countertop. But once you do that, here's your horizontal launch velocity, 0.9 meters per second. You have this thing you're looking for. This range is actually your horizontal displacement during the flight. Okay, and this is an unknown. Well, other horizontal information, what do you know? You have to remember that for projectiles, there is no horizontal acceleration. The horizontal component of the motion is constant motion, so your acceleration in the x direction is 0. That's handy to know. But something we don't know is how long it takes to travel this horizontal distance. Time is an unknown right there. But there's more that we understand here. We have some information about the the vertical velocity right at launch. So this is like an initial vertical velocity. I'm going to redraw that guy because it's too sloppy. Initial velocity in the y direction. Well, since it's a horizontal launch, this initial velocity is 0 meters per second. Now, this height of the countertop, this represents your change in the y position. So that's h. Now, in this case, your countertop is easily measured at 87 centimeters above the floor. And so now, well, is there more? Well, sure. Your acceleration vertically for projectiles, that is going to be little g. It's a constant, and it's always going to be that for your vertical acceleration. So we get 9.8. Now, I know your textbook likes to use 9.81, but I'm even going to let you know this little secret. On the AP exam, you're allowed to use 10 for little g. And so I wouldn't worry about the 9.8 versus 9.81, not at all. But again, time is an unknown here. We don't know how long it takes to follow that vertical distance. So we got to start figuring this guy out. So let's try this. Let's start with the goal, right? Let's start with looking at that thing. Can we figure this out? Well, we have a relationship. Since the horizontal stuff is constant motion, velocity in the x direction is equal to the change in horizontal position divided by the time. Well, therefore, this answer we're looking for is velocity in the horizontal direction times time. But we need time. And in order to find the time, you have to remember that the time of flight is not determined by horizontal stuff. It's dependent upon your vertical information. So we'll use our vertical info. And that's what we're going to do. So here we go. Our vertical information. Well, let's see. We have vertical initial velocity. We have vertical displacement. We have vertical acceleration. And what time? We need some sort of equation, some sort of mathematical relationship between those things. And here you can start to see why it's so beneficial to list information that you know. because once you get it listed, you can start to say, well, I really need an equation for these things. And it turns out we have a nice one. It's one of the big five. And so you remember this. There's going to be, let me get into my thoughts here for a second. Okay, so it's going to be this change in the y direction, change in the y position, which is really h, but we'll come to that. Well, this is equal to your initial velocity in the y direction times time plus 1/2 acceleration in the y direction times time squared. You can see we have related the change in the vertical position, the initial vertical velocity, the vertical acceleration, and the time. And in this case, time will be our unknown. But let me do this real quick because, well, we're using some different names. So this is an h. This is a 0. That goes to 0. That's going away. Now with the vertical acceleration being little g, now we're always going to use, as I wrote here, we're always going to use a positive 9.8 for little g. And yes, it's in the negative direction, so what you need to do is take care of that minus sign out here in the equation. It's nice to do it this way. So there's 1/2, and then little g, and then t squared. And this looks like an equation we can solve because we know little g and we know h. Let me rearrange this so we get the time is equal to 2 times h divided by g. And you may be wondering, well, why? Because I'm going to get a minus sign under the radical. Well, actually, you're not. If you think of this change in y position, you're really, it's a downward change. And so this is truly a negative 87 centimeters right there, right? And so you have this negative value here and this minus sign here, which end up canceling out. You do not have a negative under the radical. It works out. So now this becomes a simple situation. I have to convert the centimeters to meters. 87 meters, 2 times that. I'll put my 2 here so it fits. And then g, 9.8 meters per second squared. And the time comes out to, rounding off, 0.42 seconds. Well, okay, now, that's handy dandy because I needed that. I needed time to work this guy out. So this is a quick matter now to say, aha, well, delta x, and this is really my range that I'm looking for now. Range is delta x, and that's equal to horizontal velocity times time, and now I know both of those numbers. Horizontal velocity, well, that was my 0.9 meters per second. I have that extra 0 there just for consistency in my sig figs. And the time, 0.42 seconds. So I get this range of 0.378 meters. And so sig figs, 0.38 meters. Boom. Done. I was able to figure out how far this thing would land away from the countertop with some basic information and my understanding of how the horizontal component of the motion works versus the vertical component of the motion. And the link is time. Excuse me. So what they have in common, these two times, I don't want to use that color. Here we go. These two times right here are the same time. The time it takes to move this horizontal distance to the point where it lands is the same time that it takes to move from this vertical position to the floor. Time is what links your horizontal and your vertical information together. All right, well, so I want to ask you something though. In this situation, what if we had things a little bit backward in terms of our initial information? So we have this situation here. We have this initial velocity in the x direction. There's an h, right? And there's a range where it's going to land. Okay. So, what if that's our unknown, right? And yes, I know there are methods to find that up on a horizontal surface, but what if you're not sort of looking at that? What if you're only looking at the projectile motion part that's taking place, and you want that initial horizontal velocity? Could you use a stopwatch and a meter stick? Well, sure, but what if I restricted you even further? What if you used only a meter stick, which measures distance? Could you get that velocity? Well, I don't know. I want you to think about this. I'm not going to tell you the answer, but this is something I want you to consider. Look at the situation, because you know for this velocity you're going to need what? You're going to need this horizontal change in position, which is basically your range. Well, you could measure that. And you're going to need time. But you can't measure time. You can only measure distances. Hint, hint, hint. Okay, I'm going to leave you with that. I'd like you to think about that and try to figure this one out. I'll give you the answers later on. Give it your best shot. Thanks for watching. I will catch you next time.